Hi, sorry, I'm a minute late. My calendar didn't notify me for some reason.
No, you're good. Okay. Welcome to the Titan Robotics Club Astronomy webinar. Titan Robotics Club hosts a series of webinars surrounding a variety of different careers. Our webinars are posted on YouTube, so make sure to check out our YouTube channel. And this one will be posted on it as well. So if you're interested in getting involved with robotics, join a first robotics team near you. And if you have any questions, just put them in the chat and we'll answer them at the end. So now we'll be introducing our guest speaker, which is Dr. Agol. Yeah, feel free to share your screen.
I'm sorry about that. I'm unmute myself. Hi, everybody. Thanks for inviting me today. And thanks for the questions in advance. So I'm Professor Eric Agol from University of Washington. And let's see, I have a set of slides prepared to describe my research path and career and then the research that I'm doing, which I'm spending the most time on. So I've been at the University of Washington for almost 20 years. And in the past, I spent a lot of time studying black holes, but for my recent research is really focused on trying to detect and discover planets that orbit other stars. These are like solar systems beyond our own solar system. And the diagram at the bottom shows an artist's impression of a planetary system that it helped find one of the planets for. So first, I'll start with a bit of my biography. I did my high school in California. I grew up in the San Francisco Bay Area and went to high school in Oakland at the College Preparatory School. And from there, I didn't go too far for college. I went to University of California at Berkeley and graduated in 1992. And I studied math and physics there. I actually never took an astronomy course while I was an undergraduate at UC Berkeley. At that point in time, I was planning to become a theoretical particle physicist. And I enrolled or applied to programs in that area and was accepted at the University of California at Santa Barbara. And so in 1992, I started at UCSB to do theoretical physics. However, before that, I had a summer job that happened to be in astronomy or astrophysics, and that got me really interested in that topic. And so during my PhD, I actually switched directions and went into astrophysics instead of particle physics. And from then on, I've been an astrophysicist or an astronomer, depending on which term you prefer. And so after my PhD, oftentimes in research or in academia, you have to get experience to become a professor, which is what my eventual goal was. And so I did 2 3-year jobs at one was at Johns Hopkins University in Baltimore, Maryland. The second one was at Caltech in Pasadena, California. And both of those involved studying black holes, which is the subject of my dissertation. And then finally, after my second postdoc at Caltech, or during that time, I received a faculty job offer from the University of Washington. So I've been here since 2003. And so again, this is I'm in the midst of completing my 20th year at the University of Washington, which is kind of amazing. It's gone by quickly. In the process of studying black holes, I actually got interested in the phenomenon of gravitational lensing. And then from that, I started getting interested in studying extrasolar planets. And so that's been the main bread and butter of my research for the last decade plus now at the University of Washington. So I'll spend most of the slides here talking about that. Please feel free to raise your hands or interrupt me if you have any questions or if there's anything I didn't explain clearly enough. And of course, I have a list of questions from y'all, which I'll get to after this. My research now involves the detection and characterization of extrasolar planets. And as you've already heard, this is generally gets shortened to exoplanets. And this means any planet that is exterior to our solar system. I have participated in discovering planets. One of those is the fifth planet in the Kepler 62 system. I'll talk about the Kepler spacecraft, which was used to discover this planet. And I actually was the one that found the Rainbow data, which was missed by NASA, basically a bug in the algorithm. And at the time, it was the most similar planet to Earth that we'd found. So a pretty exciting discovery. Since then, I've helped in discovering another planetary system called TRAPPIST-1, which has 7 planets orbiting a very small star. And so I'll talk about that more today. And the thing that I've probably spent the most time on is a technique called transit timing variations, which I'll briefly talk about. And that's a way that we can use transiting planets to not only measure the sizes of planets from the depth of the shadow that they cast, but we can also measure the masses of planets from their dynamical interactions, which causes slight variations in the orbits, and that leads to a change in the time of their transit as a function of time. Now, in our solar system, we have 8 planets, not counting Pluto. And these basically come in 2 varieties, the terrestrial and the gaseous planets. The gaseous planets also you can divide into 2 varieties, the gas giants and the ice giants, Jupiter and Saturn, Neptune and Uranus. Amongst all these planets, of course, we have our very special one, the Earth, which is the only currently known, I should say, habitable planet in our solar system. There was one question about whether we might find life elsewhere in the solar system. I think Mars is probably the best place to look, but there are lots of astrobiologists and planetary scientists looking anywhere they can look in the solar system. And what's interesting is that when we started looking for planets around other stars, our first expectation was that these planetary systems would look just like our solar system. And that idea has been completely blown out of the water. We find exoplanets come in all shapes and sizes, and they come in varieties that we don't even have in our own solar system. And so planetary systems, first of all, seem ubiquitous. They're very, very common around other stars. And secondly, they show a huge range of variety in their properties, and they can differ quite dramatically from our planetary system. Now, this was anticipated a long time ago, even before 0 BC. There were some philosophers who thought about the possibility of planets around other stars. More recently, Gerardo Bruno had postulated that because there's all these stars out there, and because they're like our sun, why wouldn't they have countless Earths all rotating about their stars or their suns in exactly the same way as the 7 planets in our solar system, which is the number they knew at the time. And the fact that we see suns because they're the largest bodies and the most luminous, Bruno actually inferred that the planets remain invisible to us. And that's still, for the most part, true today. We have detected some light from planets around other stars, but most planets we detected indirectly via the shadows they cast or via their effect on the host star. And Bruno said the countless worlds in the universe are no worse or no less inhabited than our Earth, which is a really bold statement to say that these other planets might be places that life could exist. And so in searching for exoplanets, we do hope to find different examples of different varieties of planets. We hope to find clues about how planets form in the first place and the different paths to formation that can take place. We'd like to find out how special our Earth is. And again, as Bruno was suggesting, maybe look for the signs of life on some of these other exoplanets. Now, there's been clues for quite a long time, I would say many decades now, that there are planets around other stars. And one of these clues comes from looking at stellar nurseries. This is a picture from the Hubble Space Telescope of the Orion Nebula. And you can see the glowing gases that are formed by young stars that are surrounded by gas. These young stars are very hot, and they basically light up that gas like a neon light. And then you also see smaller stars, which are those, you can see those kind of little white fuzz balls. 3 of them are zoomed in the inset in the upper right of the screen. And around those, you can see these glowing little cocoons, which are called protoplanetary disks, or proplyds for short. And it was interesting when these were found because these look exactly like what we would expect for our very young solar system. As a star collapses from gases to form, it can start to spin faster and faster, and that spin can create a disk around the star. And that disk is what we think that planets form out of, and that explains a very simple property of our solar system, that our planets all seem to lie very close to the same plane. Now, the first exoplanet around the sun, like our star, took many more years to find, even after we knew about these protoplanetary disks. And so the first one was found in 1995. It was a huge surprise in that this planet orbits around its star once every 4.2 days, which is extremely fast compared to Mercury, which is long as 80 days. And so this was a surprise because not only was it a very short orbital period, but this planet also had a mass that's about half the mass of the most massive planet in our solar system, which is Jupiter. And that's surprising because how could you form a planet that close to the star? The gases would have been too hot to condense and form a planet. Our explanation now is that that planet probably formed further out and then gradually spiraled in to its current position around its star. On the right-hand side, you can see the detection data. And each of those little dots with a air bar sticking up out of it is a measurement of the Doppler shift of that star. And the Doppler shift is caused by the motion of the star around the center of mass of the planet. And that motion is what allows us to indirectly infer the presence of the planet. And so the star and the planet are doing this dance around one another. The planet goes in a rather wide orbit and the star in a rather small orbit around their common center of mass. And it's that star's motion around that center of mass that allows us to infer the presence of the planet. So this was a really exciting discovery. And when it was made, it basically changed astronomy, and that now astronomers realize we can find other planetary systems around other stars. Now, given how close it is to its star, this planet is way, way too hot to have liquid water. It's also probably a gas giant planet like Jupiter, and so it probably doesn't have a solid surface like Earth. And so astronomers hoped that we might find more similar planets to Earth. One of the key properties of Earth is the presence of liquid water on the surface. And that liquid water, of course, can form steam, which creates clouds. That steam can rain, creating water droplets from which we get our rivers and lakes and oceans, ultimately. And then, of course, towards the poles of our Earth, we can have water in its condensed form in the form of ice. And so our Earth is a very special place in that the temperature allows for these three different phases of water. And water seems to be pretty critical for life. It's a very good solvent. It is present in all of life. We're mostly made up of water, as you all know. And people have speculated you might have non-water-based life, but nobody's really figured out how chemically that would work. Water has a lot of really special properties. And so it's hard to imagine life without water. And so one place that astronomers are trying to look for life is in places where we can find water. Basically, follow the water is the mantra. And this has also led to a concept called the habitable zone, which is kind of a misnomer. It doesn't mean that a planet necessarily would have life on it or be inhabited, but it's a concept that involves the possibility that you could have liquid water on a planet. In other words, the right distance from the star, the right amount of greenhouse warming to keep that surface of the planet in the right range so that water could be in its liquid phase. This also doesn't necessarily mean that these planets need to orbit sunlight stars. So we can look for planets around different types of stars, but a star with a different, say, luminosity, which is basically a wattage of the star telling how much power it outputs. If it has a lower luminosity, the planet would have to get closer to be warmed enough so that the water, if it's there, wouldn't freeze on the surface of the planet. And so there's a range from away from stars, which we refer to as the habitable zone. This is a diagram showing this habitable zone, and the horizontal axis shows an orbital distance that a planet would have relative to its star, and then the vertical axis shows the size of the star in relative to our sun. So both of these axes are relative to our Earth and our sun. Our Earth on the horizontal axis has a distance of 1. This is something we call an astronomical unit. It's basically like our foot or our meter basis of measurement for the distance of planetary orbits. We all measure them relative to the Earth's proximity to the sun, which on average is called 1 astronomical unit. And then the vertical axis shows stars of different masses going down from half the mass of our sun up to twice the mass of our sun. The blue kind of S-shaped region is a rough estimate that planetary scientists have calculated, where if you had the right atmosphere on the planet, you might have the ability for that planet to host liquid surface water. That doesn't mean the water has to be there. It doesn't mean that the atmosphere has to be there. But if the planet in that blue zone had properties similar to our Earth, with our tectonics, which produce CO2, which we know is a greenhouse gas, and if there was water present, which seems to be pretty ubiquitous throughout the universe when the conditions are right, then planets orbiting at that distance could potentially have surface liquid water. So a lot of our astronomers have focused on this habitable zone as a region to look for Earth-like planets. You can see our sun on this diagram on the left has a mass of 1 solar mass by definition, and then all the planets are spread out in our solar system. The sizes of the planets and the size of the stars are highly exaggerated in this diagram, so just so that they're visible. If they were to scale, then you actually probably wouldn't be able to see them because they'd be really small dots. So just to a word of caution in interpreting this diagram. And you can see that the Earth is the only one in the habitable zone in our solar system. However, some calculations indicate that the outer edge of this habitable zone should be a bit further out, and that Mars maybe at one point have had the right atmosphere, that it could have had liquid water. Right now, Mars is a very thin atmosphere. It does have carbon dioxide, which causes some greenhouse effect, but it's much too thin to have current liquid water on the surface of Mars. So the approach I've taken to studying exoplanets and trying to look for Earth-like planets around other stars is called the transit technique. This is a very simple concept. The basic idea is you wait as a planet orbits the star, which is shown by this gray curve around this yellow sphere, which is supposed to represent a star. As the planet goes in front of the star, it blocks some of the light of the star. And so when we measure the brightness of the star, that brightness might dip. In this example, it shows a giant planet, which is about 1/10 of the size of the star, which could be similar to our sun in this case. And that means that the area ratio is 1/10 squared, or 1/100th. And so as the planet goes in front of the star, you'd see the star get dimmer by about 1%. And so the axes show time and brightness. The little dots are actual measurements, and they show some scatter, and that's due to what's called quantum noise. It's basically as we count photons, the number we count at any given time can fluctuate a bit. And then the orange curve is a model. That's something that I've worked on calculating. Some of you asked about computer algorithms, and something I spent a lot of my career on is trying to develop very fast and accurate computer algorithms to create models like this orange model that's shown in this diagram that fits this data. Note that this vertical axis is highly zoomed in. This 1% dip is a very small dip, and so you have to zoom in to be able to see it clearly, like in this diagram. If you were to plot it from 0 to 100%, then this dip would just be a very, very small change in the depth or of the line going across. And what this line represents is basically we stare at the star with a telescope and measure its brightness as a function of time, and so that's what each of those points are. If this dip repeats itself every orbit of the planet, then we know that we've detected an exoplanet. And so that's how the transit technique works. It does rely on chance, though. So not every planet's orbit is going to pass in front of the star. If the orbit was more inclined, then it would go above and below the star, but you'd never actually get a transit. And so we have to get lucky. And if we observe enough stars, some of those planets' orbits will be close enough to edge on that they will pass in front of the star. And that's how we detect planets, using this technique. This technique has been around a long time. This shows a painting from 1639 of an astronomer named Jeremiah Horrocks, who used telescopes to observe the sun and watch Venus and Mercury go in front of the sun. And so those planets blocking the light from the sun create what's called a transit. In this picture, you see the disk of the sun and you see the little shadow cast by a planet. When we look at exoplanets, which orbit other stars, those stars are so far away, we can't see their disks. We only see a point of brightness from that star. And so that's why we have to rely on the brightness of the star changing with time to detect the planet. So that's a key aspect of this technique. I'll pause to see if there are any questions.
Oh, there's a couple of questions in the chat.
Okay, sorry, I don't have the chat up. So
yeah, I'll read them out loud. So the first one is from Jacqueline.
Okay.
Are there any solar systems with more than one sun?
Yes, there are. And then, unfortunately, I had some slides on that, but I don't have them in this current presentation. But yes, we see what are called circumbinary planets. Most stars actually are not like our sun. Most stars actually have a stellar companion that orbits around them. And some of these are called binary stars, binary for two. And so with two stars orbiting each other, in some cases, if the stars are close, you might have a planetary system that orbits around those two stars. And we found maybe a dozen examples of that, where we have two stars orbiting close to one another, and then we have planets orbiting around those stars. And I helped participate in the discovery of one of those circumbinary planets. They're called. Circum means around, and then binary means that there's two stars. Astronomers nickname those Tatooines because the planet Tatooine from Star Wars. When you see the picture of its star in the film, of course, it's actually not one star, but two stars. So that is an example of a fictional circumbinary planet system. That was a good question.
Okay, thank you. And then another question is, why do people on the southern end of Earth not see everything upside down?
Because they're not standing on their heads, is the answer. Yeah, so from the southern perspective, you do see a different sky. And so actually, if you want to study the whole sky as an astronomer from Earth, you have to put telescopes in the north and in the south, because the Earth blocks the view of the southern sky for us. So like we can't see the Southern Cross, we can't see the Large and the Small Magellanic Cloud. I traveled down to Australia, and it was really cool doing that when I was out in the outback, because I got to see the Magellanic Clouds with my naked eye, and without a telescope, and also see the Southern Cross, which is pretty cool.
Yep. Okay, thank you. And then there's a pretty long one. So in our solar system, scientists have speculated that there might be a possibility of life in underwater oceans,
Yeah.
On like the moon of Jupiter and Saturn, which aren't in the Goldilocks zone. Does that mean that there could be life beyond the habitable zones of stars?
That's an excellent question. Yes, the habitable zone is a very Earth-centric concept in that it involves kind of surface liquid water. But if you put water under enough pressure, if you put ice under enough pressure, it can become liquid at higher pressures. And so the idea that's being asked about is the possibility that Beldis or I just want that moon or the other moon. There's a couple. Europa might have liquid water beneath their surface. So the surface would be ice, but down below, where the ice is under enough pressure, it would actually become liquid again. And there may be some layer within those moons where you might have liquid water. And so that could be also be true of exoplanet systems. We may have exoplanets that are far enough away that the surfaces would be icy, but there could be liquid water below the surface. The same might be true of Mars, actually. Mars might have liquid water below the surface, and astronomers or planetary scientists are looking for that. So yeah, that's an excellent question. So the habitable zone is a very restricted concept, and there may be many other places where life could exist. Might be kind of hard to find if it was deep below the surface, though. So astronomers are kind of focused on the surface liquid water idea, and that's where the habitable zone concept comes in. Yeah,
Yeah.
that's a really good question.
And then earlier you talked about the binary systems with two stars. So
Yeah.
could the transit method or like other methods be used to detect extrasolar planets?
Yes, and we've detected circumbinary planets with the transit method, and that was actually done with this spacecraft, which I'm showing on this slide here, called the Kepler spacecraft. It stared at 150,000 stars for 4 years straight, and you can see a diagram of its detectors, which are basically their digital cameras, just like the ones in a cell phone, except they are really big digital cameras and they cover a huge area of the sky, which is shown in the little squares that are on this sky map on the right hand side. And so what the Kepler spacecraft did is there's a diagram on the left which shows a solar array and its sunshade, and that front of it opens up and allows it to look at the sky. It actually just stared at this one region of the sky for 4 years straight and measured the brightness of 150,000 stars continuously over 4 years. It took a measurement every half hour. And so if the planet was to go in front of one of these stars, it could detect its transit. There are about 12 of the stars, which were binaries, which showed dips due to the stars blocking one another's light as they orbit around each other. But it also showed extra dips at different times that we interpreted as being due to planets. And that was confirmed by the fact that those repeat over the planets. So we actually did find some circumbinary planets with this. We also found thousands of single stars that have planetary systems. And someone asked whether there's multiple planets, and yes, I think there was a question about whether some stars have multiple planets. We see up to 7 planets orbiting a single star with the transit technique around some of these stars. So this Kepler spacecraft really revolutionized our study of exoplanet systems, finding thousands of planets with a wide range of different properties, from very small to very large, and very short to very long orbital period.
Okay, thank you.
Yeah.
Yeah.
I was actually lucky enough to find a planet in the Kepler data. How am I doing on time, by the way? Oh, I see some other questions in the chat now. Okay, I'm going to come back to some of those questions. How are we doing on time?
I think, yeah, we're good.
Okay, sounds good. So this shows an actual data set that I used to discover a planet. I basically wrote a computer algorithm that looked through the light curves of stars and looked for little dips. And then every time there was a dip, it would create a spike in this light curve. Some of these spikes are just due to noise, like the random fluctuations in the amount of brightness of the light. The x-axis, I'm sorry, it's not labeled here, but this shows time, and these are in days. So you can see this is over about 3 or 4 years. And then the vertical axis basically tells you how significant the dip is that was detected with the Kepler spacecraft. And what you see is that there are 3 spikes here. I don't know if you can see my cursor. They're outlined with these red dash curves. And these lined up in time perfectly, that there is exactly the same amount of time between this spike and this spike as there is between this spike and this spike, 367.3 days. It turned out that I had discovered a planet orbiting a star. Now, there was already a known planet that was closer to the star, and this one had a period of 122 days. You can see the quantum fluctuations I talked about earlier, which is these dots, the fluctuations in the brightness of the star. Its average value is shown as 1 here, but there's fluctuations that are about 2 parts in 10,000 or so. And that's because these stars are fairly faint, so we don't get a lot of light, and so that causes larger fluctuations. But you can see that there's a very distinct dip here due to this planet. And this one has a depth that's only about a few parts in 10,000. So this is a very, very small planet. It turned out this planet's about 60% bigger in diameter than our Earth is. The planet I found is the second one at 267.3 days. These had some initial names that they were given, technical names. And this one actually was a bit shallower, which means it's a bit smaller than this other planet. And it also had a longer orbital period. Well, it turns out that these 2 planets are accompanied by 3 inner planets. They're labeled as B, C, D, E, and then the one I found was F. This shows the configuration of these 5 planets at a single point in time. 2 of them are behind the star, 1 is in front of the star, and these 2 others are off the star. And this is a roughly the color that star would appear if we could see it by eye. But it's much too far to see by eye. We just see a little point of light with the Kepler spacecraft. And we see these dips as the planets orbit around and go in front of the star and that repeat themselves. So it turned out that this planet, at the time I found it, was the most similar to Earth. So this shows some artist impressions of what the planet sizes might be. Kepler 62F is, again, just a little bit bigger than the Earth. It's about 40% bigger, maybe 40 to 50% bigger in diameter compared to the Earth. And so this was a pretty exciting discovery that happened a little over a decade ago. And so this means if you plot this habitable zone, like I showed earlier, this shows a wider range of stellar mass from 1/10 to 1 times the mass of the sun. And this shows, again, the same orbital distance relative to the Earth. The solar system is here with Mercury, Venus, Earth, Jupiter, Saturn, Neptune. And then the Kepler 62 system has a slightly lower mass for its star. And then the orbital distances of 62E and 62F at 122 and 267 days are shown right here. They're both within this liquid water habitable zone. Now, we don't know if these planets have atmospheres, so that's a big caveat. But if they did have an atmosphere with enough carbon dioxide in it to cause greenhouse effect, water actually is a greenhouse gas as well, they potentially could have surface liquid water. And so that's something that astronomers would like to look for, but presently we don't have the technology to make precise measurements like that. But this was a pretty exciting discovery because it may be a very similar planet to the Earth in some ways. Now, something else we can do to better search for Earth-like planets is look around even smaller stars. There's a class of star out there that's called ultra cool dwarf, which is extremely small, very low mass, and very small size stars. They're also extremely red because of the low temperatures at which they emit light. The fact that they're so small means that if you saw a transit of a planet in front of an ultra cool dwarf, you would see a very large dip. So an Earth-sized planet around one of these small stars would show a 1% dip, while around the sun it would be like 0.01%, like barely perceptible on this diagram. And this diagram is highly zoomed in. And so this means that if you look for Earth-like planets around small stars, you actually have a better chance of detecting these planets. And the habitable zone is much closer to the stars. So the orbital periods of the planets in the habitable zone are very short, so you don't have to wait as long to detect them. So this was an idea that inspired a survey that was led by a group of Belgian astronomers. They dubbed it the TRAPPIST survey. Transiting Planets in Planetesimal Small Telescope was the acronym that spells out the word TRAPPIST because there's a famous type of Belgian beer that's brewed by Trappist monks in Belgium. So this acronym was made as a nod to their Belgian roots. They built 2 telescopes, one in the southern hemisphere, one in the northern hemisphere. Like I told you earlier, you need to look in the south and the north to cover all the sky. So one was placed in Chile and one in Morocco. And these telescopes had infrared sensitivity. One of the telescopes is shown in the upper right, and then in the lower right is what it looks like at night within the dome of that's surrounding the telescope. And this TRAPPIST survey looked at 50 stars, and they found 2 planets orbiting one of these stars, and they called this TRAPPIST, the TRAPPIST-1 system, the first planet system found by the TRAPPIST survey. We actually followed this up with some data from one of the NASA telescopes called Spitzer. And what we found was incredible. We found 7 planets that transited this star. And in just a second here, this is a diagram showing a simulation of the orbits around the star. And then this shows what it would look like from our perspective. The top is just an artist's impression of what this might look like. The bottom is the actual data. Again, you can see those little white points are the measurements of the star's brightness. And what you see is that some of those white points rain down, and that's when a transit's occurring, when one of the planets passes in front of the star. You can also see some brightenings. Those are called stellar flares, when the star gets a little bit brighter briefly. There's also gaps in the data, and that's when the data was being downloaded from the spacecraft, or the spacecraft was trying to look at something else. What we saw in this system, the TRAPPIST-1 system, were 7 planets orbiting all within 19 days or less. The shortest orbital period is 1.5 days. So this was a really remarkable discovery. And it turns out that about 3 or 4 of these planets orbited within the so-called habitable zone of this star. So that was a really exciting discovery for that reason. This inspired some artwork. There was actually a Google Doodle and showed right here, and there was a musical album and some books that were written about speculating what this TRAPPIST-1 system might look like. But what astronomers are excited about is that this gave us the ability to characterize these planets very precisely. Because the star is so small, we can actually measure these planets' properties very precisely relative to the star. There's a really cool video. I won't play it, but let's see, I can provide the link later. It's called TRAPPIST Sounds, and it basically says, has looked at what the TRAPPIST-1 system would sound like if you were to give each planet a different note to play. And it sounds kind of melodic, actually, but I'm not going to continue playing it. But anyways, the planets seem to be arranged in this very cool progression of chords, and that makes it sound kind of musical. So there's kind of a harmony to this system. Here's another update of the habitable zone diagram with the TRAPPIST-1 planets way down here. These orbit a very low mass star, and the habitable zone is extremely close. And so these planets actually orbit around the star from 4 days out to about 9 days for the planets that are potentially habitable. Again, we don't yet know the atmospheric composition of these planets. We also don't know whether they have surface liquid water. There are 2 closer planets in the system, and there was a news announcement just Monday, actually, observing the closest planet, which is labeled Planet B, with the James Webb Space Telescope, and that showed that that planet doesn't have an atmosphere. But we are using JWST or Webb to study these planets. It's a really large telescope, and it's giving us really precise data. So we're going to have some news about that coming up in the next few months. This shows the JWST telescope as it was being assembled. You can see how massive it is compared to the humans that were putting it together. We'd like to know if these planets do have atmospheres, and if so, those atmospheres, do they contain water? Do they look like, this is a actual picture of the Earth and the Moon from afar. We'd like to know if they look like that. And we won't be able to do that for a long time, but one thing we can do with JWST is to look at the planet's atmospheres. And the basic idea is that that atmosphere is kind of a ring around the planet and will block some of the light from the star. And certain molecules will block light at certain wavelengths. And so we can use that to look for those molecules, kind of fingerprinting the composition of the atmospheres. Some of you might want to get involved in this research. Astronomers love to share their love of science with folks. And technology has really made it possible for lots of people to get involved in astronomy with digital cameras on their telescopes. It's even made technology made even satellites cheaper. And so you don't need to really have a PhD to get involved in the search for exoplanets. This is one example. There's a project called Panoptes, which allows you to purchase a very inexpensive telescope. In fact, they'll help subsidize that, and you can take observations of other planetary systems. There's also one called Unistellar, which is very similar. There's some cases where astronomers have too much data to look through, and so they look for amateurs to help look through the data. And so if you want to go to planethunters.org, they oftentimes have data that can be looked through, and you can try and find your own planet in the data, much like I found in the Kepler data. So if you'd like to explore the range of planetary systems out there, there's several websites, and I can provide these links to you later, that have databases on the different planetary systems that we've discovered. So that's all I I have to share today, and I'd love to field some of your questions now.
Yeah, there's a couple more questions in the chat.
Okay, great.
So the first one is, how are neutron stars different from regular stars? Could a neutron star have planets orbiting it?
Yes, that's an excellent question. So neutron stars are essentially dead stars. They're stars that have gone through their nuclear burning and they've used up all their nuclear fuel at the center, at which point they stop burning. And because of that, there's no more heat left to support that star. And so it just collapses in itself. And this process creates an explosion at the same time. And so the outer parts of the star are blown out into space as a supernova, but the inner part of the star collapses and becomes extremely dense. And so the mass of that star gets concentrated in an extremely small area, something like the size of Seattle, would be the size of a neutron star, that has the mass of our sun. So this is like very, very, very dense. So neutron stars are extremely different from a regular star. They don't have fusion going on to power their energy, and they're extremely dense and also very, very small. What's interesting, though, is that some of these neutron stars pulsate. They have magnetic fields that are created by the formation of these neutron stars, and those magnetic fields can act like a radio beacon and send out radio pulses. And astronomers detected these, and we call them pulsars, actually. There's one system that was found in 1992 to show evidence for planets orbiting around a pulsar. And the pulses sometimes arrive early, sometimes late, and we think that's because the planets are tugging on the pulsar and causing its orbit to change. So yeah, so we do know that neutron stars can in fact host planets, which is really bizarre, because if this neutron star formed from the supernova explosion, how do you get planets after that? There's a question about the benefit of using space telescopes. It's a huge benefit. So the Kepler spacecraft was so successful because it was put in space. From the Earth, when you look at stars with a telescope, the atmosphere causes problems. The atmosphere is always in motion. It can cause fluctuations in the brightness of a star, which are not due to real fluctuations in the star, but they're just due to the atmosphere's changing the amount of light that is detected by the telescope as a function of time. And so getting out of the Earth, above the Earth's atmosphere, is extremely critical for trying to detect very small planets, because it's that precision that enables you to see very small dips in the brightness of a star. And that's what enabled the Kepler spacecraft to detect the Kepler-62 system and other systems like it. The TRAPPIST-1 system, though, was found from a ground-based telescope. And the reason for that is that the dips are so much greater because the star is so small. So looking around small stars can allow you to get that, to do that with ground-based telescopes instead of going to space. There's a question about getting involved in professional astronomy through UW. If you come to the University of Washington, we have a program called the Pre-Major in Astronomy program. And it's also abbreviated PREMAP, which is for first quarter students to get involved in astronomy research. So if you do come to the University of Washington, I highly recommend you look that up. There's a question about a planetary nebula. Planetary nebula, it has nothing to do with planets. It turns out it's actually a misnomer. And the reason planetary nebulae were called planets initially, were called a planetary nebula, is they kind of look like a planet initially, but they're not a planet. What they are is a star towards the end of its lifetime starts to shed its outer layers. And so you get this glowing sheath of gas around stars. And that, when astronomers found them originally, looked like these little kind of blurry blobs on the sky, and they mistook them for planets. So planetary nebula stuck as a term, but it actually doesn't involve a planet. It actually involves gases being emitted by a star. These are stars that are not big enough to create a neutron star, but eventually they'll become a white dwarf star at the center, and then the outer layers get blown up into space and get incorporated into the gases within our galaxy. There's another question about a stellar magnitude. A magnitude is basically a way that astronomers gauge the brightnesses of stars. And it's a logarithmic scale because our eye is kind of logarithmically sensitive. And a magnitude originally was basically started with the brightest star in the sky counting downwards. And so the way magnitudes are defined is that the smaller the magnitude is, the brighter the star, and then the larger the magnitude is, the fainter the star. And now it's actually been calibrated to a pretty precise system instead of just being by eye. But that's a way that astronomers keep track of the brightnesses of stars. Why is the dot bigger than 0 than at 6? And I'm not sure I understand that question, but that might refer to one of the figures from my talk. Are there astronomy or astrophysics internship opportunities that you know of for high schoolers? I just heard of one, and I am happy to forward that to you. I think it's at the Space Telescope Science Institute in Baltimore, which is the institute that runs the JWST and Hubble space telescopes. So I'm happy to forward that to you. I don't have the link right now, but please feel free to send me an email. And I'm happy to pass that on to you. The three-body problem talked about the dark forest theory of whether or not we should seek out other intelligent life forms. What do you think would happen if we made our presence known in the universe? Well, I think we're making our presence known whether we want to or not. We're creating all these radio signals on Earth, which get sent out into space, and so we have lights on Earth, which creates a potential signal that could be detected elsewhere. Probably very difficult to detect, but nevertheless, it's something that for some photons out into space that alien life could potentially detect. And I have no idea what would happen if aliens detected us and whether that would be a good or a bad thing. But given the vastness of space and given the specialty of Earth, my best guess is that if there were alien life out there, it would probably be microbial. It probably would not be intelligent or able to come and conquer Earth. That's my guess, but that is maybe incorrect. So who knows? That's one of the reasons we have to go out and look, is we don't know the answer yet. Not that we have to go out and look, but a lot of people want to go out and look and see if we can find the signs for life elsewhere. We would be able to detect Earth-like signals or radio waves from the current exoplanet. That's an excellent question. There are astronomers looking for radio waves from exoplanets, and we actually see this phenomenon in Jupiter. Jupiter interacts with its moons, and the magnetic interactions actually create radio waves that we see from Jupiter. And so some folks have speculated that maybe stars and planets interact in that way and might create radio waves from that interaction. So astronomers are looking for that. Okay, the question about the dot after 6. At 0, dot being bigger at 0 and smaller at 6 was for the star magnitude. Oh, okay. Yeah, so the that slide showing the magnitudes is probably showing that astronomers use this weird system where 6 means that stars are fainter and 0 would mean that they're brighter. In more complex solar systems, how would the Doppler effect work? Well, the Doppler effect actually shows the motion of the star around the center of mass. If you have multiple planets, then they all change that star's motion around the center of mass. So you can kind of get this kind of spiral graph, like loop-de-loops of the star's motion around the center of mass. And so that complicates the Doppler shift. But we can actually detect multi-planet systems with the Doppler effect by looking for the contributions from multiple planets at different orbital periods to the motion of that star, which is a really great question, because we found actually some systems that have up to 7 planets with the Doppler effect as well. What would happen if the gravitational pulls from multiple planets cancel out? That's also a good question. Each planet should be in a separate orbit, so we can distinguish those planets by the fact that even though they cancel at sometimes, as the planets orbit around the star at different rates, then that's going to change their Doppler effect, and so that you don't get a perfect cancellation at other times. In fact, sometimes you'll get an enhancement. And so as long as you monitor the star long enough for multiple orbits of each of the planets, you can actually distinguish those. These are really good questions, by the way. I also have some in my email that I'm happy to take a stab at. How did I discover the passion for science, and what's my advice to today's adolescent who spends a lot of time on technology devices, but not necessarily technology itself? Well, I think my passion was actually ignited through mathematics. I really like mathematics. I actually have an identical twin brother who's a mathematician. And math is a really useful tool to have for science because a lot of science is quantitative. Computers are also very useful. And so having some computer science or computer programming skills is really useful. I use computers in my work all the time. We use it for analyzing data, for creating models. A lot of my code is open source. I have a GitHub repository if you want to look through it. I've started using a language called Julia, which I really like. All to say that I think a passion from science can come from reading a lot, from being out in nature, from using a telescope to discover astronomy. Astronomy really is a fun way to engage with science, and to get all the way to getting involved in research projects and watching documentaries about science, etc. So I think there's many ways to get excited about science that don't necessarily involve technology. There's another question: how many planets do you believe there are yet to be discovered? The answer is too many to count. Within our observable universe, does everybody know Avogadro's number? Something like 6 times 10 to the 22. It's the amount of molecules in a mole of a substance. So it's something you learn about in chemistry. And roughly speaking, there's something like an Avogadro's number of stars in our visible universe. That's within probably a factor of 10 to 100 or so. We can't count all those stars directly. And if each of those stars has a few planets, maybe 5 to 10 planets orbiting it, that means that there's more than Avogadro's number of planets out there waiting to be detected. Now, many of those are too far. The stars are too far away, or the planets too faint to be able to ever detect. Really, we're only able to search our solar neighborhood for planets, and so in our solar neighborhood, which is maybe what this question was getting at, there probably are still thousands, maybe millions of planets waiting to be discovered. The number of planets is actually rising rapidly with time that we've detected, and so that I think will continue for a long time. There's a European Space Agency mission called Gaia, which is about to, I think, is poised to discover thousands and thousands of planets. So we'll keep adding to that, and they'll keep growing. But I think my speculation, I guess, is in the next couple of decades, we may have detected upwards of 1 million planets, which would be pretty cool. Let's see. How do I apply software to astronomy? So I use software in a lot of different ways. One is for analyzing data. So some of those plots I made were created with software that I've written. And I also use it for writing algorithms to process data. So a lot of data processing is done by astronomers. And then I use software also to code up mathematical functions, which are too complicated to calculate by hand. So you need to calculate them on a computer. And I spend a lot of my time doing that, developing algorithms and then implementing those algorithms in different languages so that myself, but also other astronomers can use those. And some of the algorithms I developed have been used by astronomers around the world to discover and characterize thousands of exoplanets. So that's some of the work I'm most proud of, actually, is the software development.
Sorry to interrupt. There was another question in the chat.
Oh, great.
What's the difference between a white hole and a black hole?
Okay, yeah. So a white hole is something that's more science fiction-y, that it would be kind of like a black hole in reverse. But we don't know of the existence of white holes. So it's a concept that is more kind of a mathematical science fiction concept, maybe, but we don't know any way to create that nature would create a white hole, which would be kind of a black hole in operating reverse. It would be, a exploding rather than compact. So white holes are, I guess one way to say it is that there's something that some theoretical physicists have speculated about, but no, there's no way that we thought of that they could be created in nature. Can black holes explode? That's a very good question. Black holes we think can explode through quantum processes, but we think that this would take a very, very long time, like much, much, much longer than the age of the universe. If the universe somehow made very small black holes, like say the mass of like a large mountain, then that sort of black hole could explode rather quickly, like in billions of years instead of 10 to the 40th years or something. So, but we don't know of any way that nature would create such a small black hole. So in principle, black holes could explode. In practice, that probably hasn't happened in the history of our universe. It probably won't happen for a very long time. I see a few other black hole questions. If gravitons existed, I think they would travel at the speed of light. How would they get out of a black hole? And does the strong gravitational field of black holes prove that gravitons don't exist? Well, gravitons are still kind of a topic of study, in that this is a hard question to answer, and that involves describing quantum mechanics and general relativity. But we basically have these two theories of physics, the quantum theory of physics and the general relativistic theory of physics. And physicists have not figured out how those two theories work together. Quantum physics describes things on a small scale extremely well, and general relativity describes gravity and things on a large scale very well. But nobody has been able to apply the concepts of quantum physics to general relativity. But there's speculation that if you did, then just like in quantum physics, we have a quantized particle called a photon, which is a quantum of light. You could also have a quantized particle of gravity, which would be called a graviton. Now, there is kind of, astronomers think that gravitons probably, or physicists think that gravitons probably do exist, but and we think that they are created, and the way that they're created, actually, one example of how they're created is by a change in the gravitational potential. And so let's say you have two black holes orbiting each other. Those two black holes are warping space, and as they move around, that warping of space changes with time. And so those two black holes would send out what we call a gravitational wave. We've actually detected gravitational waves, dozens of them over the last decade or so. And those gravitational waves are produced by merging black holes, and also we've detected merging neutron stars. We think that those gravitational waves are comprised of gravitons. And so it's the motion of black holes which can create gravitons, but those gravitons are created outside the event horizon of a black hole, so they can escape. They wouldn't be trapped by the black hole. I don't know if that precisely answers that question, but that is the basic idea is that the gravitons will be created outside the black hole by its distortion of space around it. Looks like a few other questions are in the chat there. What would happen if a black hole exploded? You basically would get a burst of very high energy radiation, gamma rays. And we actually see gamma ray bursts in the universe, and there was some speculation for a time that those might be exploding black holes, but that actually doesn't match what we see. We actually think that those gamma ray bursts are created by merging neutron stars and by exploding stars. If the edges of our universe are expanding faster than the speed of light, how will JWST be able to uncover the origins of the universe? Okay, that's a good question. So JWST can only explore within what's called the horizon of our universe, which is the region throughout our universe from which light is able to travel to us. And because light travels at a finite speed, that limits how much of our universe we can probe. We can't see beyond that. And that's called our cosmic horizon. So JWST will only be able to study what's within our cosmic horizon. But as it looks back in time and looks outwards in space, it can get closer and closer to that cosmic horizon. And so it'll be able to learn more about the universe when it was younger and younger. So it's not going to be able to probe the origin of our universe per se, because it can't look at what happened at really early times. It can only go back to maybe a few 100,000 years at most, or at the earliest after the creation of the universe. So it can understand more so. It'll help us understand the origins of galaxies and stars in our universe, and that's a really exciting topic. But it won't necessarily tell us how our universe formed. Is it possible there's a gap in general relativity, which is why we don't know what dark matter and dark energy are? That's a really good question. So there is an idea called modified Newtonian dynamics, which is MOND for short, which is the idea of that general relativity is wrong and it needs to be modified, and this modification is going to explain dark matter. To make a long story short, I don't think MOND holds any credence. First off, it has problems mathematically that haven't been resolved. Secondly, a lot of the concepts in MOND actually don't match what we know about the early universe. Nevertheless, some astronomers and physicists are holding on to that idea and trying to use it to explain dark matter. There are some physicists that have tried to modify general relativity to explain dark energy. The simplest way is to add something called a cosmological constant, which Einstein actually had in his original version of general relativity. But we have no idea what produces that cosmological constant. It's a complete mystery. It does seem to exist, actually. We have evidence from that from supernovas, but we don't really know what causes it or what it's due to. So that is a modification of general relativity, is to add in this cosmological constant, but it's still a mystery what it is. What's the oldest star that astronomers have found? Ooh, that's a good question. I don't know the exact answer to that, but there are stars that we're seeing in distant galaxies that are formed, very close to the Big Bang, probably, a few 100 million years after the Big Bang. But I don't know the exact answer to that. All right, so I think I'll wrap things up given the hour.
Yeah,
thank you so much. Thanks for the questions. It was a lot of fun, and I really appreciate your inviting me to come speak. Some of the questions that I couldn't answer, feel free to follow up with an email, and I'll try to answer those. And I'm also happy to give those websites to you all.
Okay, thank you. And then thank you everyone for coming to the astronomy webinar. We'll be posting out on YouTube, and make sure to keep your eye out for more opportunities in the future.
Yeah.
Yep. Thank
That's
you.
good. All right. Thanks.
Thank
Good to
you.
talk to you all. Take care.